In the last video in this series, number 15, we introduced the idea of Kruskal coordinates, with which we were able to explore the space-time around a Schwarzschild black hole in 2 dimensions of space-time. The beauty of those coordinates was that, despite the distortions of space and time around the black hole, they always illustrated the velocity of light as travelling at 45 degrees at any position on the diagram, in other words, at any event in the space-time. Using those coordinates, we were able much more easily to interpret the communications between objects travelling radially near a black hole or hovering on a shell near that black hole, as one of them saw light coming from the other or received radio communications from them. However, as with all the space-time diagrams that we've been considering so far in this series, even with the simple space diagrams early on, they were drawn with a black outer edge. And this black border was only for convenience to limit the extent of the axes of any graph. Clearly the space and time axes each extended to infinity, and the black border was simply to give a cut-off for the purpose of drawing. And this was true even for the case of our blue Kruskal coordinates RK and TK, which could be used to identify events in the space-time, as well of course as for the red R and T Schwarzschild coordinates plotted in those Kruskal coordinates, which could also be used to measure that same space-time around the black hole. In such diagrams, we can't plot events or see things in the whole of space-time out to infinity, obviously. However, we've thought enough about converting from one frame of reference to another to be able to say that it should be possible to change from the Kruskal coordinates to another new frame of reference where measurement readings are squashed up, so that, in a sense, infinity could somehow be pulled in and drawn as a single point or line on a graph. What I mean is, there are plenty of mathematical functions which tend to a finite number as their independent variable tends to infinity. One such example, although there are many, is the hyperbolic tangent function. A plot of y equals hyperbolic tangent x looks something like this. In other words, as this x goes off to infinity, positive or negative, the function hyperbolic tangent of x will tend towards the finite values of +1 or -1. If we were then to use this kind of function to change our Kruskal coordinates from the blue RK and TK to some new variable, say RK tilde and TK tilde, it would mean that they would always have finite values, even when the original coordinates were to get extremely large. If, at the same time, we could ensure that in using the new coordinates, light would be shown to be travelling at 45 degrees, then we would have compressed the whole of this two-dimensional space-time into something that could be drawn on a finite flat surface, and we would still be able to draw any ray of light as a line at 45 degrees. A coordinate transformation that would do those things and would work both inside and outside the Schwarzschild radius would be something like this, which uses the hyperbolic tangent function. These mauve RK tilde and TK tilde, which have maximum sizes of 1, are in a sense the Kruskal coordinates squashed into having finite values everywhere. This would mean that if we were then to take this new set of mauve axes, RK tilde and TK tilde, and plot the red Schwarzschild coordinates onto them, it would produce a new readable graph of the whole of space-time out to infinity of space and the infinity of time, both the past and the future. Before we do that, here's a reminder of what we have at the moment in our Kruskal coordinates. The red Schwarzschild coordinates have, in a sense, already been distorted once by plotting them in the blue Kruskal coordinates. This whole region represents outside the event horizon of the black hole, and the hyperbole for the red R are measurements of position, whilst the radial lines for red T are measurements of time, and they both, of course, extend to infinity beyond the boundary of the black border. Let me now recolour those time axes light blue, simply in order to distinguish them more clearly. This region represents inside the event horizon of the black hole, where the red measurements of time and space have been reversed. Let me also recolour these. I'll make the hyperbolae, which are now time axes, grey, and the radial lines, which now represent distance, orange. From now on in this short discussion, try to remember that all of these coordinate lines, red, light blue, grey and orange, should all really be red, and I may even inadvertently refer to them as red coordinates, meaning the old Schwarzschild coordinates. With this coordinate system, each of these regions seem not to be useful to us in connection with space-time around a black hole. We may return to them later, but for now we could say that the meaningful space-time shown here is really this. Okay, so if we now use a coordinate transformation such as this to change the blue Kruskal coordinates rk/tk to the compactified mauve coordinates rk tilde and tk tilde, we will get something like this, with the whole of this space-time from r equals 0 to r equals infinity, and from t equals minus infinity to t equals plus infinity, has been squeezed to fit into this finite diagram. Of course, with this diagram we don't really need the outer black border anymore, because the diagram contains all of meaningful space-time. What we do need to do, however, is to think about what the various bits of this diagram mean, including the lines around the edges of it. You can see here that the singularity has been drawn slightly differently, and this is in accordance with a particular mathematical convention, although it could be drawn in other ways. Let's assume that this zigzag line now represents r equals 0, but is essentially as it was before. This is the region outside of the Schwarzschild radius, and this the inside. The boundary between the two, the event horizon, is once again shown with these thicker red lines, which are still at 45 degrees. In that sense, it looks exactly as it did before when we were using the Kruskal coordinates to plot our red coordinates, and this is because, if you recall, the horizon followed a path of light, and changing to these new compactified mauve coordinates has maintained the direction of light beams to be at 45 degrees. Light beams travelling radially inwards will follow paths such as these, coming from possibly large radial distances away, and they will travel in straight lines towards the horizon, which is the thick red line. They will also continue beyond the horizon towards the singularity, although of course if measured using the red coordinates they would seem never actually to reach the horizon, which has a red t-value equal to plus infinity. Let me remind you, these green lines are all beams of light travelling along the same radial direction. Remember, we only have one spatial dimension here. Some can be thought of as being in front of or behind others in time. Also, if you recall, this lower thick red line also represents the horizon with red r equals rs, but it has a red t-value of minus infinity. As well as being part of this extreme distorted red hyperbola, this lower line is also part of the extreme blue curve at the bottom. This lower thick red line is sometimes called the anti-horizon, because any outward going radial light can only travel away from it and never towards it, but we'll think about that a little more later. Notice how in the region of where r and t are both small, the red r lines and light blue t lines look much as they did before they were compactified. The r coordinates look hyperbolic, and the t coordinates seem to be straight lines. The compactivation to the mauve coordinates has not really changed things at small distances and small times, and this should seem reasonable from what we know about the hyperbolic tangent function, which was used to compactify things. For small values of x, the hyperbolic tangent of x approximately equals x itself, and so there's not likely to be much difference. However, at large distances, the red spatial hyperbolae start to curve in the opposite direction. And similarly, at large positive or negative times, the time coordinates in blue here, rather than being straight lines, curve wildly. And this is obviously because the diagram is trying to depict infinite values of r and infinite values of t in a finite diagram. Now, it should also be mentioned that these three particular points in the diagram are sometimes given special names. The top one is called future time like infinity. Time along both these lines is equal to plus infinity. In a sense, the two straight lines, shown now in light blue, represent the extreme blue curve of t equals plus infinity. And this point at the apex here is where all spatial points, all the r values, come together in the diagram at t equals plus infinity. For similar reasons, the lower vertex is called past time like infinity. All the spatial values are drawn converging at t equals minus infinity. The vertex on the right is called space-like infinity. Again, these two straight red lines on the right represent the curve for the infinite value of r, and this point is where all values of time, all the blue curves, both positive and negative, converge at r equals infinity. As mentioned earlier, these two extreme lines on the right also represent infinite times. The upper one is part of the blue curve for t equals plus infinity, and the lower one for t equals minus infinity. That means we can put these labels on them. The upper line is known as future null infinity, and the lower one is past null infinity, and you'll sometimes see them referred to as script I plus and script I minus, simply from the way the analysis was performed originally. This future null infinity line refers to r equals infinity at t equals plus infinity, and the past null infinity line is for r equals infinity at t equals minus infinity. And this whole thing is called the Penrose diagram for a Schwarzschild black hole, that is, for a non-rotating, uncharged black hole. It enables us as outside observers to appreciate the whole universe from the singularity at r close to zero up to an infinite distance away, and also from time equals minus infinity to plus infinity. You should remember that all the red, light blue, grey and orange curved lines here represent the red ones which we've been using with the Schwarzschild metric. Although in such diagrams the lines become closely packed near the edges and therefore are impossible to analyse with any accuracy, the diagrams can be extremely useful in thinking about and in interpreting a number of gravitational phenomena. Let's look at a few trajectories within this kind of diagram. If a ray of light came in on a radius from infinity, then it would have started somewhere on the line labelled past null infinity, r equals infinity, t equals minus infinity, and then along a trajectory such as this, shown by the green line. Obviously it would make its way eventually to the black hole and on to the singularity, even though someone using the red coordinates would say that it stopped at the event horizon, where red t equals infinity. But what about these two trajectories which represent two objects, A and B, which each have mass? I've drawn them coming from the infinite past, but from similar positions not too far away from the horizon. A may well have accelerated or decelerated while on its journey, but it's clearly seen at later times heading towards the event horizon and the singularity, either in free fall or perhaps powered in some way. The object B, on the other hand, looks as though it is hovering a fixed distance from the event horizon at all times, as it seems to be on one of the red curves. As you'll realise, on diagrams such as these, it's impossible to tell exactly where things are at large distances and times. However, in the region where we can distinguish things, B is almost certainly on a red curve and hovering some distance away from the horizon. Take note, though, that the fact that B looks as though it is approaching the horizon up here is deceptive. If B is definitely on the red curve, it will be keeping a fixed distance, a fixed r, from the horizon. Once again, all the r values of the whole of this space will meet at time equals plus infinity up here, at future time like infinity, and so distinguishing what's going on in this region is difficult. Finally, if B at this point were to send a beam of light to A, shown by the green arrow at 45 degrees, the diagram helps us appreciate where and when, and indeed whether, that light would be received by A, in this case just before A reaches the singularity. Now, before looking at the way in which Penrose diagrams can also be used in relation to flat space-time, it might be worth a quick mention about white holes. The Kruskal coordinates for the region around a black hole look like this before compactification to the Penrose diagram. In this diagram, we've clearly only put the Schwarzschild coordinates in what we might call the meaningful regions of space-time, shown here with both R and T sets of lines drawn in red. Once again, the event horizon at r equals rs is shown with thicker lines, thicker red lines. However, when first discussing this kind of thing, we did say that the mathematics suggested coordinates in the other regions as well, which include negative r, whatever that means. Now, if all of this picture of space-time is compactified like before, using a formula that would bring the infinities into finite values, then with the consequent mauve rk tilde and tk tilde axes, we would get a diagram which would look something like this. This seems to show what appears to be another universe with another singularity. Whereas this represents the region of the black hole within its Schwarzschild radius in what we might call our universe, this could be said to represent some sort of parallel universe which has what has been termed a white hole in it. As with our universe, this parallel universe has two horizons, one to the black hole and one to the white hole. On top of that, the two universes seem to be connected in some way. The apparent connection between the two is at the centre where the two horizons meet, and this is called an Einstein-Rosen bridge. At first sight, it would seem that it might be possible via a black hole to travel to another parallel universe. However, the Einstein-Rosen bridge is what's been termed a non-traversable wormhole. A simple way to appreciate this non-traversability is to try to imagine how travel from the universe on the right to the parallel universe on the left could possibly take place. Even travelling at speeds close to the speed of light, an object with mass could, at best, approach the other universe travelling on a trajectory shown with this brown line, which would eventually take it, of course, into the black hole and not into the other universe. There's no way that the object, or indeed a beam of light, can have a trajectory with an angle more shallow than this in order to enter the parallel universe, or indeed to enter the white hole. It's perhaps interesting to note that light from anywhere in the universe, shown here in green, can only travel either outwards to infinity or inwards and into the black hole, and any light within the event horizon is doomed to enter the singularity. There's no way into the white hole or into the parallel universe. Similarly, light in the parallel universe can only travel either to infinity or into the black hole via the parallel horizon, whereas it would seem that light within the horizon of the white hole can only travel outwards either into the parallel universe or into what we might call the ordinary universe through the anti-horizon. You can also play around with these ideas in connection with objects with mass, travelling at speeds close to that of light, and you'll reach the same kind of conclusions. The difference, of course, being that such objects can hover and stay still as far as the red R and T measurements are concerned. In every case, however, there's only a way into the black hole and no way out once past the event horizon, and there's only a way out of the white hole and no way into it. And this kind of reasoning, that one thing only lets something enter while the other thing only lets things exit, gives rise to the idea that perhaps the black hole is some sort of wormhole into the other parallel universe. It would seem in this case, however, that, as mentioned earlier, this Einstein-Rosen bridge is indeed a non-traversable wormhole. It's worth saying that other theoretical research has found mathematical descriptions of seemingly more realistic wormholes for other situations, and you can read up about those if you wish. And now on to flat space-time. The idea of using compactified Penrose diagrams is not, of course, limited to space-time which contains a black hole, or indeed any dominant mass. One can also apply it to flat space-time. One simply needs to use some function like the hyperbolic tangent used earlier to shrink the infinite scales of space and time to something more manageable. Let's think about doing just that. We will start with a flat space-time, and the most convenient metric to consider is when the space is being measured using spherical polar coordinates, those which use r, theta and phi. When we discussed these earlier, we realized that these coordinates are curvilinear in theta and phi, but because of the spatial symmetry we can ignore both of these angles and simply work with the one space direction, the radius. And so once again we start with this illustration of flat space-time, with the frame of reference of the outside observer shown in red, radius r against time t. This is flat space-time and there are no masses here, and so of course we are free to use a Cartesian type grid for the r and t, like this. Even though we have no black hole here, it's clear that the region labelled negative r is still somewhat meaningless, because we're not treating radius as a vector, but simply as a measure of the distance in any direction from the origin. However, we will now have to think a little more clearly about this. When we did have a black hole at the origin, it was obvious that nothing travelling on the radius inwards, even a beam of light, could get to the other side, to negative values of r. And it didn't really make sense anyway. However, now that we have flat space-time, clearly an inward beam of light, which I'll draw here slightly above the axis for convenience, would actually pass through the origin and increase its r value in the negative r direction. Now that's not a problem in one sense, because we're simply measuring the size of the distance from the origin, but it will affect how we draw our space-time diagrams. In a way, a light beam coming into the origin like this, having hit the point r equals 0, would have to be interpreted as then coming out from the origin like this. We've only got one dimension of distance after all. It's as though the light had been reflected. At least that's what our measurement with this particular system might seem to imply. That means that a light ray coming inwards like this on our flat space-time diagram would have to be drawn like this after it passed through the origin. Notice that both beams are at 45 degrees. The Cartesian grid is equispaced. If the beam had arrived at the origin earlier, then it would have been recorded like this, and earlier like this. We obviously still won't be using the left-hand side of this whole diagram, but we may have to get used to a kind of reflection, which isn't really a reflection, but a passing through. Okay, so that's what happens to light. But a similar kind of thing will happen to objects with mass, which are travelling radially through the origin. In these cases, of course, the angle will be different and will depend on the velocity of the object. Now there's one more thing to think about before we compactify these coordinates and see how such a flat space-time can be compressed to form a Penrose diagram. What we've just looked at so far has been things travelling along a single radius in and possibly straight out the other side, and of course that straight out was drawn as a kind of reflection. However, this diagram will also allow us to draw the path of things that miss the origin, in other words things that do not travel on a radial line. Now you might at first think that that must involve theta or phi, but in fact it needn't, as we will try to justify now. If we simply look at the space around the r equals 0 point in 2 dimensions, we would have something like this: simple two-dimensional polar coordinates. There's no time here in this diagram, just flat space, and it's obvious where the 0 or origin is. And I suppose you could say that the coordinate r appears multiple times in this, and if we wanted to record the position of something in this space, we would, strictly speaking, need two coordinates r and an angle, say, theta. However, if we just wanted to appreciate the r value, the size of r, we could perhaps see that from this diagram. What I mean is, imagine a beam of light just missing the origin like this. We could probably say that when it was coming in and still very far away, the beam would more or less be travelling along a single radius, and I mean extremely far away. Also, when it was very far away and going out, it would more or less be travelling along a different radius. On the other hand, when it is near the origin and going past, the beam of light would be on differing directional radii, but at any instant it would always have a definite but varying value of the radius r, here, 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 and so on. And this would be its distance of closest approach to the origin. That means that with our simple space-time diagram, as we're only plotting the size of the radius against time, the path of such a beam of light could be plotted like this. In this case, it doesn't so much give the impression that it is reflected from the origin, but rather it seems to be deflected some distance away. Now don't be confused, this has nothing to do with hyperbolic curves and the like. It is the much more straightforward trigonometry issue of angles, which comes about from the way we are choosing to display the distance r. The same thing, of course, will also happen to objects with mass which go near but not through the origin. It's just that their initial and final angles will be more steep because they can't get anywhere near the velocity of light. So having thought a little bit about how things will look in this ordinary flat space-time, let's now compactify this red r and t system using the same kind of formulae as last time. This uses, as I say, the hyperbolic tangent and will convert the red r and t into what we'll call the mauve r tilde and t tilde, the compactified coordinates. Once again, there are other functions that would do this, such as the inverse tangent, all with very similar looking results. More or less whichever method is chosen, our red RT flat spacetime, or at least the right hand side of it, all the way to infinite positive and negative times and way out to positive infinite radii, would be squashed to this, where the result is shown without the black border. After all, it now displays all of this two-dimensional space-time. For extra clarity, I will put the new red timelines in light blue so they can be distinguished more easily. Now, even though the new mauve r tilde and t tilde may only go up to a magnitude of 1, the red r goes up to infinity, and the red or light blue t goes from minus to plus infinity. Once again, the various parts of this diagram are given certain names which relate to the values of r and t, like this. And if you think about them, each of these labels should be fairly obvious by now. The red r equals 0 axis is on the same line as the mauve r tilde axis, and the red t equals 0 axis here in light blue is on the same line as the mauve t tilde 0 axis, just as you'd expect from making substitutions into the various conversion formulae. Also, there is little change in the vertical r and horizontal t lines near the origin when t and r are small. They're almost straight lines, again just as the formulae would predict, whereas there are massive distortions in the lines when r and t become large. Furthermore, these two lines, highlighted here in thicker red, correspond to r equals infinity. Before compactification, it would have been a straight line vertical here out at infinity, and this system has brought it into an extremely tight curved line, essentially two straight lines. These two lines also, separately, must be the last of the blue time curves, as time equals plus infinity for the top one and minus infinity for the bottom one. Once again, in this flat space-time, any light rays coming in on a single definite radius will be plotted as though they are reflected off the origin at r equals 0, and they would be drawn at 45 degrees. Radial objects with mass would be similar but would have a steeper angle, a lower velocity. On the other hand, objects or light which travel towards but not directly towards r equals 0 will be plotted with some sort of curved shape showing the distance of closest approach. And this idea that the whole of space-time, even flat space-time, can be illustrated on a finite sheet of paper may seem interesting at first, but many students soon begin to think that it doesn't really tell you much that you didn't know already, and the crunching up of coordinate lines at large distances makes it difficult to see any detail anyway. However, Penrose diagrams are in fact very useful when trying to think about causal relationships in general relativity, particularly in the region of a black hole. And they give an illustration which can be helpful in appreciating what some of the equations are saying. Okay, having spent some considerable time in the last few videos on the Schwarzschild black hole and the various ways of describing it and measuring the space-time around it, we now want to return to the main thrust of this series of videos, which is to get to grips with the Einstein field equations. By now we should recognize that this one-line equation, when applied to four-dimensional space-time, will represent 16 4 times 4 equations. Also, within these equations, we know from our studies what these constants are, and we've discussed in detail the metric tensor, but we've not yet touched upon any of these: the Ricci tensor, the curvature scalar, and the stress energy momentum tensor. Once we've dealt with all of these terms, we can think about what Einstein's field equations mean and why they are the way they are. So, in the next video we will begin the process of discussing this Ricci tensor and the curvature scalar. This will be done by first thinking about something called parallel transport, and then using that idea to introduce another tensor, the Riemann curvature tensor. Now, this Riemann curvature tensor is not actually used in Einstein field equations, but we'll see that from it we will be able to derive the Ricci tensor and the curvature scalar, both of which will be needed for those equations. This video number 16 has discussed Penrose diagrams, but in the next video number 17 we want to get back on track and think about Einstein's field equations, and to prepare for that we'll discuss the Riemann and Ricci tensors as well as the curvature scalar.